Thank you guys very much. Nice presentation. Next, we have from the University of Florida, Aguacero, presenting their ultra water treatment.
Hello, ladies and gentlemen. We are Team Aguacero, and we're here to present today a solution to Cuba's drinking water problem. This is my team. I am Jose Serra.
My name is Pedro Perez.
I'm George Cooney. I'm Braden.
And as I said, we are Team Aguacero. So without further ado, the introduction. The challenge we seek to address is that of providing access to clean drinking water to all of the population of Cuba. The current population of Cuba exceeds just over 11 million people. As of 2012, only 77% of the island has access to clean drinking water via centralized plumbing. And in rural areas, that number drops to only 58%, leaving 42% of the other population in the hands of other sources, many of which are unreliable and pose health risks due to contamination. As we all know very well from grade school, water, in addition to food and shelter, is necessary to sustain human life. The inability of the current infrastructure to provide clean drinking water to all the Cuban people is a violation of basic human rights and the issue that we wish to address today. As you can see here, this is where we've got our statistics from the WHO. This is the total population of Cuba. 77%, as you can see here in 2012, has access to clean drinking water via centralized plumbing, and 58% in rural areas.
After more than half a century of command economy totalitarian rule, Cuba fails to confront the ineffective distribution of water in a sanitary and efficient manner. Three challenges to the availability of potable water are the main projects that we need to address. One is environmental, the other one is infrastructural, and the other one is epidemiological. As a result, many Cubans... Environmentally, the absence of water as a result in climatological fluctuations of rainfall have caused droughts in many provinces of the island. As a result of this, many Cubans have resorted to home cisterns and unsafe water containers for the storage of water. Consumption of this staunch water has led to an increase in waterborne parasites and infectious diseases. As a result, in 2012, there was a cholera outbreak in the island where more than 600 Cubans were sick. Infrastructurally, outdated collecting distribution facilities have challenged the distribution of water. The use of 1,522 chlorine plants throughout the island failed to eliminate diseases once the water leaves the treatment plants. The Cuban Academy of Sciences has noted that the 400,000 citizens of Havana are supplied by an aqueduct constructed in 1893, foreseen for only 200,000 inhabitants.
All right. So the main challenges we have with accessing clean water in Cuba are the water scarcity, the lack of alternative water sources, the obsolete distribution system currently in place, and the increasing population, which has created more of a demand for water. What we find with the current piping system is that about 55% of the water being supplied is actually lost due to leaks. And on top of the faulty pipes, the pumping stations have also proven unreliable due to breakdown of equipment and also the lack of backup pumps. Because of its location in the Caribbean and its geography, Cuba is especially susceptible to the effects of climate change. In recent years, Cuba has been victim to droughts, which have severely depleted the freshwater reserves. Watersheds provide more than 65% of Cuba's available water and make up more than 80% of the potential water supply. The lowered precipitation amounts have resulted in the storage of fresh water in surface water bodies to reach only 43.1% of the max capacity per year, which is about 6.5 billion cubic meters.
Our proposed solution. Our proposed solution aims to solve the problem of access to clean drinking water by setting up a pilot water treatment and bottling plant in the Cotorro municipality of Havana, capable of serving up to 2.7 million people. Our project is intended to serve the people of Cuba with clean bottled drinking water while existing infrastructure is expanded upon and brought up to a level where it can serve the entire country by bottling treated water into 5-gallon jugs and making it available to consumers in markets, restaurants, schools, hotels, and businesses. To provide this clean water, the pilot location was chosen in Cotorro because here there exists a pumping station that can be repaired for use in this project. Water pumped from the station can then be filtered using a slow sand filtration process followed by UV sterilization, after which the treated water is then bottled immediately to avoid recontamination. Containers are then loaded into a small fleet of trucks purchased for this operation and sent out for delivery to markets and other establishments for purchase by the consumer, who upon purchase returns his or her empty container for reuse. Based on its performance, the pilot would then have to be scaled up 4 times to serve the entire population of Cuba. At such a time when the country's infrastructure is capable of providing water through a permanent means, the plants would continue to operate, now marketing bottled water as a commodity, much like a Dasani or Zephyr Hills type of company. Sorry.
All right, so, so how it works. Okay, there we go. So for this project, we'll be using a slow sand filter. Slow sand filters are sometimes referred to as biosand filters. These names refer to filters that use biological agents in the sand to filter the water instead of chemical agents. So the water first passes through a diffusion plate, and then will pass through what is called the biological layer, also known as a Schmutzstick. The word Schmutzstick comes from German origin. It means dirt cover. Commonly referred as the biolayer. The biolayer is responsible for removing 99.99% of pathogens. The biolayer is formed through a process called ripening. And ripening is basically we flow the water through the top layer, through the bottom, then back up. That's done for about 3 to 4 weeks, and after that process, a 5 to 10 centimeter thick biolayer is formed. It is important to note that the biolayer must always be submerged in oxygen-rich water. If it is not submerged in oxygen-rich water, then the biological agents in the biolayer will die, and the filter will no longer work. So after the biolayer, the water would then flow through the sand and gravel layer. Fine sand filters are better than coarse sand filters and offer more resistance to water flow. So for this project, we'll be using a filter built out of fine sand, and we'll have about 3-foot layer of sand, about 6 inches of gravel on the bottom. This will allow for a flow rate of about 0.1 gallons per minute per square foot or less, and the effective size of the sand lies between 0.35 millimeters and 0.15 millimeters. After the water flows through the biolayer, sand, and gravel filter, it will flow through the outlet pipe, which will flow onto a sanitized ramp, and then will be treated with UV rays. The UV lighting kills harmful organisms that the slow sand filter could not, such as Salmonella E. coli. And the way UV light works is it damages the RNA and DNA of the microorganisms, which prevents it from replicating. And after UV treatment, the water will be ready for bottling and distribution.
So because of the nature of our sand filters, the only harmful product we actually find is the sludge that's being produced from the biolayer. And to dispose of the sludge, we typically let it dry off in order to prevent it from polluting other nearby sources of water. And then after treatment, the sludge can then be purchased by farmers for dressing for their land, or as well to condition some hard clay soils. To also reduce the need for producing sand, we have an alternative, active filter media, which is made from recycled bottled glass, or glass bottles, that can be used instead. And this will help create a smaller carbon footprint. So for health impacts, as we know, water is required by the body to regulate temperature, lubricate joints, protect tissues, get rid of waste, and much more. Supplying potable water to the Cuban people will ultimately bring about numerous health impacts. And We all know clean water is vital to our survival. Some harmful bacteria can thrive in untreated waters. For instance, as we mentioned earlier, Vibrio cholera. And Cuba has had an extensive history with cholera outbreaks. Recently, in 2013, the Pan American Health Organization reported 678 confirmed cases of cholera in Cuba. And basically, in short, what we expect is for citizens to no longer be exposed to this dirty drinking water, and those will limit the spread of disease.
The social and political impacts of this program will interconnect the citizenry and elected officials in a future free Cuba. It will provide a correlation between socio-economic development and the move towards or solidification of a democratic institutions. It guarantees health, social, and political stability. And economically, it provides incentives that will lead to more innovation in a free market society. Economic impacts. It will provide financial resources to entrepreneurs and provincial laborers. It will help capacity building technology, provide societal confidence in the economy, leading to increased personal expenditure and market growth. It will secure workers' economic stability with an average salary of 4 times higher than the average Cuban paid today, and many others.
Budget. The total project budget amounts to roughly $37.6 million USD to set up a pilot plant, hire workers, and purchase bottling containers and a small fleet of delivery trucks. The breakdown is seen here on this slide. It has been estimated previously in a presentation entitled Water and Wastewater Priorities and Cost-Benefit Considerations given to the Association for the Study of the Cuban Economy that it would cost $2.3 million to repair the pumping station in Cotorro. The slow sand filtration filter is projected at $7.2 million, given in an interview with the president of an American company called Blue Future for the total costs associated with setting up their highest output system, the BFF 1000. Given the intensity and exposure time needed to sterilize water with UV, it is calculated that it would take nearly 100 UV light fixtures and bulbs to sterilize the filtered water, amounting to nearly $12,500 in fixtures and bulbs. All these figures here combined add up to our grand total of $37.6 million. In summary, the inability of the Cuban government to readily supply the entire population with potable water has been an issue for many years. Whether it is due to the water scarcity caused by poor precipitation levels or the outdated and inefficient plumbing system put in place, the existing infrastructure challenge needs to be addressed. The proposed solution provides the people of Cuba with a reliable source of clean drinking water until the centralized water distribution infrastructure is either repaired or reworked entirely. At which point, the project takes on a secondary nature of selling bottled water as a commodity rather than as a necessity. The proposed solution aims to affect the Cuban people positively, economically, social-politically, and especially with respect to health, while maintaining little to no ecological harm and promoting sustainability, primarily creating jobs and demands for technically skilled people, free enterprise, and an increased standard of living with reduced outbreaks of bacterial diseases. Thank you.